Thank you, guys. I'm very excited to be here. So I'm going to be giving the whole lecture from the whiteboard. I will do my best to write large. If I lapse and start writing too small, please holler from the back and remind me. I will do my best. Okay, and so what I'm hoping to talk about today really is how superconducting qubit systems work, how you should think about them, and what are sort of the cool tricks of the trade that make these systems a little bit different from, say, the atomic or ionic qubits that Phil talked about yesterday. So I think one of the key things about these kinds of qubits is that superconducting qubits exist because of three things that came together. So the first of these is superconductivity. And so this means that if you take the right metal and you cool it down far enough, the electrical resistance, at least at DC, goes to zero. So it means you can take a standard circuit-looking pattern device and basically zero out the resistance. And so this gives you the hope for long lifetimes, because you can get rid of the naive sources of resistive loss. The other thing that comes out of this is actually that the superconducting gap limits excitations. And so the superconducting qubits that people use are actually hundreds of microns or even millimeter-sized hunks of metal. There's billions of electrons in these things, but they act like one single collective wave function, and they don't have lots of extra degrees of freedom flopping about. And a lot of that protection actually comes from the superconducting state. The other reason that they exist is something called the Josephson junction. This is a special phenomenon that we'll get into a little bit later on, but it gives you actually a way to have nearly lossless nonlinearity. And it makes the difference between having something that's a high Q harmonic oscillator and having something that is a high Q qubit. The third thing is that there is a technical window of opportunity in the microwave domain. And so if you have a qubit, you want to be able to cool it into a single state. And so like the ionic qubits that Phil was talking about yesterday have very high energies. Okay, let's forget about hyperfine qubits. Hundreds of terahertz. And so that means that you can sort of rely on them to natively be sitting in their ground state. But for solid state technologies, this is a bigger question. You would worry about having thermal excitations of the qubit constantly messing up your computation. And so what you typically want is that h bar omega q is less than kBt. You want to have, wrong way, h bar omega q greater than kBt, so that you're not worried about stray thermal excitations messing up your qubit. And so now is where you come into some technological limitations. And so at 5 gigahertz, h bar omega is around 100 millikelvin. So if you're going to operate a microwave frequency qubit at around 5 gigahertz, you need to be able to get below a temperature of about 100 millikelvin for things to work easily. And now the base temperature of a dill fridge, so dilution refrigerator, is around 20 millikelvin. And so that means that the best refrigerator that money can buy can get to a lower temperature than the characteristic energy scale of a microwave qubit. And so microwave systems can be cooled to the ground state. On the other hand, if I made an RF qubit at 100 megahertz, this is not true. So if I have a very low frequency qubit, it's really, really hard to get it cold in the ground state and well initialized for doing a computation. But you might also say, well, you know, if RF is too low and microwave is just barely high enough, why not go higher up, right? Why 5 gigahertz and not 50 or 500 gigahertz? And the answer to that, I think, is actually really a classical technology question. And so if I look at a generator, something that I would need to drive the qubit in the range of 1 to 20 gigahertz, this is what we call expensive. I live in an experimentalist world, $20,000. So this is expensive, but affordable. So I can have some of these in my lab. I can go out and I can buy them. If I start going 20 to 100 gigahertz, the cost of this is called an arm and a leg. The cost is shooting up, $100,000, $200,000. These things are incredibly expensive, and actually the cabling gets really expensive. And now if I say greater than terahertz, the answer is forget it. Doesn't exist. And there's a sort of dead zone between about a terahertz and around 200 terahertz. And this thing is called a laser. And so there is this frequency band, which in some sense from the refrigeration standpoint would be much more comfortable, right? A 1 terahertz or a 10 terahertz qubit, I can work at 4 Kelvin. A 4 Kelvin fridge costs $40,000. A dilution refrigerator costs $400,000. Like, there's a lot of reasons to want to go to higher frequency, but basically, I can't get the classical hardware that would be needed to run a qubit in that frequency range. People are working on this. People have pushed up into sort of this kind of a range, but at least my feeling really is that the field of superconducting qubits lives in this 5 to 10 gigahertz frequency range, because it's trying to go in between this 20 millikelvin base temperature of the dilution refrigerator and this 20 gigahertz limit where SMA connectors and generators start crapping out. So there's this very narrow window of opportunity in the microwave regime. And so what I want to do for the rest of the lecture here is really explain how we create a qubit that lives in this frequency range, what are our building blocks, and how we kind of put such a thing together. And so our starting point is going to be a microwave simple harmonic oscillator. This is called an oscillator, a cavity, or a resonator. These words are pretty much interchangeable. Which one you use really depends on where you did your undergrad or what field you did your undergrad in. I got my PhD in atomic QED, and so I tend to use the word cavity. People with a more electrical engineering background will use resonator, lower frequencies, oscillator. Right, but this is our basic simple harmonic oscillator, pendulum, tuning fork, mass spring, whichever one your favorite is. And the simplest that we can look at is the parallel LC in the microwave. So we have an inductor in parallel with a capacitor, shorted to ground on one side. And you can look at the voltage as a function of time. So the inductor of strength L, a capacitor of size C, and resonant frequency 1 over square root LC. And this is sort of the simplest kind of object that we can make. There are lots of different ways to do it, but a harmonic oscillator is not sufficient for doing anything like quantum computation or for the vast majority of quantum simulation because it's completely linear. And so in order to make this technology work, we have to find something else that can be added to this basic circuit to make it more interesting and more complicated. Okay. And so we need to find some form of nonlinear element. Okay. And part of the problem with normal circuits is that all of the standard elements are linear. So if we look at a resistor, then that has the equation V equals IR. So the voltage across a resistor is the resistance times the current. So that's linear in the voltage and the current. If we look at a capacitor, then the voltage is 1 over C, the integral of I dt, or charge divided by the capacitance. And then the inductor is that the voltage is L di dt. So these are all linear, they're not going to do what we want. And so what we need to build up to doing is describing the Josephson junction. So this is how these equations are traditionally written, I would say, in an undergraduate physics course. But it turns out that it's going to be a lot more useful to write this not in terms of the voltage being the independent variable, but in terms of the current being the independent variable. And so we have one case where the current is proportional to the voltage. We have one case where the current is proportional to dV dt, and then the inductor is proportional to the integral of V dt. So these are the three standard circuit elements. Foreshadowing, I is 1 over L, the integral of dV dt. And so we want to find something in addition to this set which is nonlinear. So if you look at classical electronics, there are nonlinear circuit elements. These are things like diodes, MOSFETs, all sorts of transistors. But the issue with those is that they are nonlinear only at very large drive powers. You have to put a big macroscopic voltage on them to get them to do anything. And so they're not going to tend to give you nonlinear behavior at the few photon level, which is where you would want it for operating a qubit. And so you need something else that's going to give you a very strong nonlinearity at low powers. And the something else is the Josephson junction. Okay, and so the way that you make one of these is you take 2 pieces of superconductor and you sandwich in between a very small piece of insulator. And so it's a very small tunnel barrier in between 2 pieces of superconductor. I'm not going to cover today how you actually derive how one of these things works. We're just going to go through what the effective equations of motion are. This can be found in a large number of condensed matter physics textbooks if you really want to know the constituent relation. But the key thing about the Josephson junction is that the equation that you'll get at the end of the day is that the current in a Josephson junction goes as sine of the integral of the voltage. This squiggle stands for various numerical and unitful constants, which I don't wish to bother with at this time. So this is clearly nonlinear because it's sine of the voltage. And so this is going to be our ingredient. And now, can we get some intuition by comparing this thing to one of the linear elements that we already know about? Right. And so that's what we're going to look at next. And so the actual formula is I equals IC sine of 2 pi over phi naught, the integral of v dt. This is something which is called the critical current. You can't actually have a current in a Josephson junction larger than the critical current. So if you try to pass that value, it just craps out. This is the flux quantum, h bar over 2e. It's 2e because in superconductors, the electrons come in pairs. And then this thing is important. And this quantity, the integral of the voltage, shows up so many times in the theory of superconducting circuits that it has its own name. Okay. And so there's a quantity phi, which is the integral of v dt. And this is called the generalized flux. Or the node flux. And it's also very convenient to write the alternative form where you normalize it. So 2e over h bar, the integral of v dt, which is phi over phi naught times 2 pi. And so this is the nice simple coordinate in which the equations for the Josephson junction are easy. So IJJ is IC sine phi. And if phi is small, then the current in the Josephson junction is approximately IC times phi. And so which of the standard circuit elements is going to look like this? Pop quiz. Not really. Okay. So the inductor we wrote over there has the relation that the current is proportional to the integral of the voltage. It's just that in this case, the coefficient is 1 over L. And in this case, there are some extra unitful factors in here. And so the current in an inductor is 1 over L, h bar over 2e, phi. And so what that tells us is that this Josephson junction is some form of nonlinear inductor. So if we have a small phi, then it looks approximately linear and it has the same form as we would get for an inductor, just with L effective equals h bar over 2e IC. And so you can get a lot of intuition for superconducting circuits just by thinking of the Josephson junction as a nonlinear inductor. And so if you make a plot of I versus phi, then the actual inductor is going to be straight like this, and the Josephson junction sort of peels off. And so you can think of this as a nonlinear inductor, and L increases with phi. Okay. And so now that we have that, we can go back to our favorite circuit and see what changes. Okay. And so instead of making a parallel oscillator with an inductor, we can make one with a Josephson junction. And this square with a cross in it is the standard symbol for a Josephson junction. And this is actually the circuit for a transmon qubit. Which is the most common kind of superconducting qubit that you have. And so the intuition is that this thing is a nonlinear inductor. And so it should be sort of close to a harmonic oscillator. And so these are the levels for just a basic harmonic oscillator with the same effective inductance as the superconducting qubit. But as you go to higher and higher excitation, you see that the junction is nonlinear, and it looks like it, in fact, has a higher inductance. And so what you see is that the true states of the transmon look like this. So the actual second excited state is a little bit lower in frequency than just a straight multiple of the first transition. So that is the qubit subspace of a transmon. And so one of the things that's really remarkable about the Josephson junction is that it's strong enough that this can be 5 gigahertz, and this can be 5 gigahertz minus 200 megahertz. And so you can get a huge frequency shift just from one additional excitation. And it's this anharmonicity that allows you to treat the lowest 2 levels of the transmon as a 2-level system. In comparison to certain other qubit technologies, this is not a large number. I think for an ion, the anharmonicity of the excited states is probably 100 terahertz or something like this. And so with these qubits, you have to be careful not to go too hard or too fast and accidentally wind up in that second excited state. Yes.
So he turned the circuit into a quantum system. He made a Schrödinger equation.
Yes.
And can you say anything about this? What the process is for that? Does it give us a nice Schrödinger equation?
I think what I'm about to say next will answer this question. So give me one more filling of the board, and if it's still a question, we'll talk about that. And so one of the things that I want to show you is that there's actually a very nice picture of this, not as a circuit model, which is intuitive if you come from an engineering background, but as an effective particle in some kind of potential picture. And as a physicist, that's often more intuitive than here's a circuit, crank out the impedance. Okay. And so basically, this thing is roughly a simple harmonic oscillator. And so it's sort of natural to think that you should be able to write this as something approximately in a parabolic potential. And so there's an effective particle picture. Okay, so we have a circuit picture, and what we want is a physics picture, right? And so particles, what do they have? Right? They have position and momentum. And they have potential energy and kinetic energy. And so, right, so we say there's x and p and v of x and p squared over 2m, and p is d by dx. And so you can do the same thing for these quantum circuits in terms of the right canonical variables. And so one option is that you write it actually in terms of the voltage and the current. And so you describe the kinetic and the potential energy of the circuit in terms of the voltage and the current running. This is what's more familiar from classical circuits, M&M. What turns out to be more common in the quantum circuits, I think largely motivated by the math for the Josephson junction, is you write it in terms of charge and flux. So the number of Cooper pairs and the integral of b dt, which is phi. And so those are actually going to be the canonical variables that you use to define an effective picture. And so now we can go back and look again and look at the different circuit elements, and we can look classically and quantum and make an energy lookup table. And so for the capacitor, the energy stored in the capacitor is 1/2 q squared over c. And so that's going to be written as 4 EC n hat squared. So n hat is the charge operator, and the coefficient is traditionally factorized in this way. The inductor classically is 1/2 L I squared. And so quantum, that would be 1/2 EL phi squared with EL h bar over 2E squared 1 over L, and EC E squared over 2 times the effective capacitance. And then the Josephson junction doesn't have a classical analog, but it looks like this, minus EJ cosine phi. And so for small phi, this is proportional to phi squared. So again, in the energy picture, this looks like an inductor with a phi squared, and this happens to be a cosine. And so for a transmon, what am I going to erase? Let's see. I'll go in here. And so if we go back to this circuit, there's an energy EC associated, energy scale EC associated with the capacitor, and an energy scale EJ associated with the inductor, and the transmon has EJ much, much larger than EC. And so the way that we're going to think about this is that the Josephson junction energy is going to be the potential, and the capacitor is going to be the kinetic energy. And so as a function of phi, you have this minus EJ cosine phi is your potential V of x, and 4 EC n hat squared is the analog of p squared over 2m. And then the states of the transmon are the bound states of this well. And if it were perfectly harmonic, they would be there. But because this cosine is softer than the closest parabola, which is quite a bit steeper, the higher levels of the transmon are a little bit lower than you would get from the closest parabolic potential. So does that answer the question about appropriate variables? Okay, cool. Yes. Yeah, so she asked a good question. I think I have been a little bit sloppy. So this operator that I called n hat is actually the Cooper pair, the number of Cooper pairs. It's not actually the charge, and so the charge is 2e n hat. You'll get to know that I'm very sloppy with factors of 2 and 4 and pi and apparently h bar and e. You know, only 34 orders of magnitude between friends, right? Yes, okay. And so this is, I think, for me, I find this the most intuitive way to relate the circuit picture that's usually used in the literature to describe these things to my physics intuition, And I'm not going to talk about other kinds of qubits today, but there are qubits that have an actual inbuilt inductor, and you can really understand those as a particle in a corrugated well if you use this sort of lookup table. And so you go back to your first semester quantum and find the eigenstates, and you get a good picture for what's going on inside. Another, I think, really key thing that happens in these systems is when you have two Josephson junctions in parallel. And this is a key capability that underlies a lot of the devices, and I think is pretty unusual compared at least to atomic qubits. And this is the fact that you can actually make the Josephson junction flux tunable. And so the question really is, if I have a circuit that looks like this, so I take two Josephson junctions in parallel, and then I apply a magnetic field in here. And so this parallel configuration here is called, all right, it's going to take a while. This is a radio frequency superconducting quantum interference device. Henceforth known as the RF squid. I don't want to write that out more. And this is a standard trick that we can use in the field. And so we go to this RF squid configuration with two Josephson junctions in parallel and thread a flux. And now I'm not going to go through the derivation of why this happens, but this is equivalent to having a single Josephson junction with a new and effective Josephson energy. And so if we look at the special case of equal junctions, so I'm going to say that I have two junctions, EJ1 and EJ2. Then there's a particularly simple form for this effective Josephson energy, and it's just, oops. Yeah. Okay, yep. All right, so for the special case, it's just EJ sum cosine of 2 pi phi over phi naught, where phi is the flux through here, and phi naught is the flux quantum, which is just EJ sum cosine of the little phi that we did before, and EJ sum is EJ1 plus EJ2. And so what that means is if we make a circuit like this, where instead of a single Josephson junction, I put an RF squid, then this is equivalent to the simple circuit that we started with, except that EJ effective is a function of the external magnetic field. And so we have our nonlinear oscillator, which is our sort of effective qubit, but just by applying an external magnetic field, I can completely tune the frequency of this thing. And so you can go from a picture like this, which is, let's say, large EJ, and you can change to have a much shallower potential with much more closely spaced levels. And so there's a very nice way that you can tune the frequency of this thing. In my lab, we're a little bit nuts, and so we routinely tune these things between about 3 gigahertz and 10 gigahertz, depending on which particular shenanigans we're up to on any given day. So you have a lot of frequency tunability with the oscillator, and this is a very standard trick people use either to make things degenerate, say to run a gate, or turn things on and off, adjust amplitudes and stuff like that. And I think one of the things that I sort of like about the superconducting circuit platform is you have a lot of freedom to decide what frequency your qubit's going to be at, either by choosing the size of EJ and EC or with flux tunability. This is a big contrast to the atomic qubits where they come at the frequency that they come. And it's plus and a minus, right? Every single rubidium atom and every single ytterbium ion is exactly the same. No two superconducting qubits are exactly the same, but I can sort of make them do whatever I want. Flexibility and homogeneity, they come hand in hand. Okay, how are we doing here? All right, and so then in the next part of my talk, I want to switch to thinking about how do we read out this object, right? I think I've fairly well motivated that we can make a pseudo two-level system, but how do we read it out? Because it's in the microwave. Okay, so I want to start with a more general question about how do you read out a qubit? Right? And so the oldest way is Stern-Gerlach, right? You take your innocent little qubit, you have a magnetic field gradient, you toss the qubit into the gradient, and spin up comes out over here, and spin down comes out over there, and then you smack them into some screen, and you see where it wound up. This works, A, if you're willing to fling your qubits across the room, and B, they actually have to have a magnetic moment. So I think this is the oldest way, but it's not really done all that much anymore. So that's number one. Probably, I think the most common method is fluorescence. Extra credit for anyone who can spell that. Okay. And so this is more common in the atomic qubits. And so what you sort of want to imagine is a system, is a lambda-like system here, where so this is the qubit subspace. And there's some auxiliary excited state up there. And so you drive an excitation from 0 to 2, and that spontaneously decays back down, and it emits photons out to the side, which you can then collect on some camera. And this method relies on a couple of things. So one, it relies on it not going down that way, so that it doesn't switch state when you drive it, so that you can collect lots of photons. So you need selection rules. And then there's another technical issue, which is that you need to have a camera, a photodetector, or a photomultiplier tube. You need to have some device sitting in your lab that can actually detect these outgoing photons. And so actually this particular method sort of needs high energy photons. So the way a good photodetector works is a photon comes in, kicks an electron out, you accelerate the electron, you cause much chaos, more electrons get accelerated, and then you have a pulse. But that only works if the incoming photon has enough energy to kick that first electron off. And so this is a very common thing in atomic qubits, neutral atoms or ions, because they have selection rules and they emit high energy photons in the visible or in the UV, where you can make nice photodetectors. Microwave photons are puny little things. They do not have enough energy to rip electrons out of solids, and these qubits don't tend to have good selection rules. And so this method does not work for low frequency qubits, just naively. And so then you have option 3, which is to couple the qubit to something else, which is easier to see. And then you measure the other thing. So you have to build in some form of meter that will sort of transduce the qubit state into something that you can see. And superconducting circuits lives in here. Okay, and so the technique that people use has a fancy name. It's called circuit quantum electrodynamics, or circuit QED for short. This comes from an older field, which is called cavity QED. And so cavity QED was the field of studying sort of light matter interactions. At low energies. So not blast something with a high power laser and see what happens, but trying to look at really the fundamental quantum mechanical interaction between a single atom and a single photon. Circuit QED is going to be looking at a single superconducting artificial atom and microwave photons, hence the name. And it also gets to be cool. Circuit, we figured it out. You know, the old joke of why QED is called QED. Okay. I'm fairly sure that Feynman knew what he was doing when that name was coined. At least for those of you who don't have a math background, QED is one way of writing, booyah, I finished my proof and it's done. So it's sort of nice to be able to name your theory. Yes, I win, I figured you out. Okay, and so the ingredients that we're going to have are qubit plus cavity. And this combination is going to do a couple of things. And so one is that the cavity sort of protects the qubit from the environment. Another really nice benefit is it actually gives you a well-defined control channel. To get both control and readout signals in and out. And the third purpose that it's going to serve is, in fact, readout. And so for the last 15 minutes of this lecture, I'm going to start to describe how this works. Okay, and I'll start by drawing the optical version. So the cartoon picture is that you have two mirrors facing each other with an atom in between. It could be a real atom or it could be a fake atom. And sort of the intuition for why having these mirrors here changes things is that you can think about spontaneous emission in this system. You have your atom in between your mirrors, and two different kinds of things can happen. So if this atom spontaneously emits, it could emit sideways, in which case the emitted photon escapes, right? But it could also emit into the cavity. And so then that outgoing photon bounces back and gets shown back onto the qubit. And so this photon is, quote, emitted into the cavity and bounces back. And so in this case, the excitation doesn't leave immediately. And so this is a very, very cartoon picture, but it gives you an idea that the presence of these cavity mirrors can really change how the qubit decays. And so the presence of cavity changing emission is called the Purcell effect. The other thing that you can see is that if I shine light on the atom from the side, it gets sort of one shot at interacting with the atom, and then it's gone past. Whereas if I put light in this way, it gets in the cavity and it rattles around. And so it sort of has multiple passes with which to try to interact with the atom. And so the cavity also enhances atom-photon interactions. Okay, and so this is the optical picture where I have an actual physical atom and a pair of shiny mirrors. But we can do the same thing in the microwave to have a nice cavity coupled to the qubit. And so physically, it's going to look very different. Hamiltonianly, it's going to look exactly the same. And so now let me introduce the most common kind of cavity that we use. So this is a cartoon picture. And so all of the hatched stuff is a superconducting film, and this is sitting on top of a substrate. And so these two pieces here are ground planes. And this little thing in the middle is called the center pin. And this is a coplanar waveguide resonator. For me, I find that the most intuitive way to imagine coplanar waveguide is to go back to E&M and think about a coax cable, right? So you have a central conductor on which voltage propagates, and then you have a ground plane on the outside. And so this is the pancaked 2D version of that. You have a central conductor and ground plane on either side, and it guides electromagnetic field modes along it until you get to the end of the center pin, and then they bounce back. And so this is the same kind of resonance that you would get in a finite piece of cable, but you can fabricate it in 2D out of superconducting film. And so the standing wave mode that lives in here has a voltage profile that looks like that, and the electric field is oscillatory and points out from the center pin towards the ground planes or vice versa. And so this is the kind of resonance that we typically use. Cool. So how do we get a superconducting qubit into here? Right, that's the next question. This is a cavity, and so now I have to actually draw what a transmon qubit looks like. And so our qubit actually looks like this. So this is the simplest design. 2 pieces of metal with a Josephson junction in between. And so these 2 pieces of metal form a capacitor that sets EC, and then you run leads between them interrupted by a Josephson junction. And so what you can do is just make it fit. Come back over here and you say, oh, never mind, I don't like you. So you cut out a pocket from the ground plane and fabricate the transmon inside of here. Maybe a scale bar would be helpful. 8 millimeters long. Very much not to scale. I think for many people, this is 20 microns. And the qubit, 500 microns to 2 millimeters wide. They could be gigantic. So these are sort of roughly the scale. And so you put the qubit sort of counterintuitively not at the center of the cavity, because the center of the cavity actually has a voltage node there. So you don't get any coupling. And so the qubit's always going to be at the end of the cavity where the voltage is large. And so what are the advantages of this? So the first is that the cavity sort of dominates the light-matter interaction. So it's very hard for this qubit to radiate sideways and emit photons out this way. And so most of what it's doing is really controlled by the qubit. Very easy integration. Anybody who's ever tried to do that knows that it involves complicated mechanical mount with vibration isolation, feedback servo, vacuum chamber, laser, high precision optics, something to try to hold the atom in there, and they still tend to fly away. And so here, in this kind of a traditional atomic QED system, it's actually very hard to keep the atom in the cavity. Here it stays forever. You pattern it once, and it's either alive or dead, and if it lives, it stays there. So that's very, very nice in terms of doing measurements. 3, the resonator can be used to control and read out the qubit. So all that you have to do is put another center pin over here, and so then you can send a control signal and then you can take a readout signal out that way. And because this is a very, very one-dimensional structure, you can come in on a coax cable, send in a signal, get into the cavity, and direct it back out again. You don't have the typical problem that you have when doing fluorescence detection of trying to collect as many photons as possible, even though they're being emitted in all directions. So this is very much channeling everything in one direction. Yes.
Yep.
There we go.
So I think you're making the statement that you have to put qubit to the end of the center pin because the electric field profile. I'm just thinking, can you actually excite like a higher resonator mode to actually have not a node in the middle of the resonator?
Yes. So early on, actually, people didn't sort of realize this trick. And so they used the second harmonic mode and put the qubit in the middle. And it turns out that that's just sort of non-ideal from a microwave hygiene point of view. The other thing is it's very non-compact. And so if we're going to end up wanting the frequency of the cavity near the qubit frequency, not too far away. And so if you want this second harmonic mode to be at 7 gigahertz, as opposed to that one at 7 gigahertz, you have to make it twice as big. And let me tell you, it's painful to make like 12 millimeter long resonators and fit them onto a chip. They take up so much space. And so this has turned out to be the more standard design. There are other qubits that actually couple inductively, that would couple to the current, and then you could put them in the middle. And so there are people that work on like ultra strong light matter interactions, and they would put them there. The transmon in particular sort of doesn't have an inductive loop in it, so it only couples capacitively. Okay, I have to kill 4 more minutes. Okay, so I think that I will just wrap up by writing down the Hamiltonian for this, and then we'll start next time by seeing how it behaves. Okay, and so we've got 3 pieces to the Hamiltonian. So there's a qubit Hamiltonian. This is familiar. HQ is 1/2 h bar omega q sigma z. This is just treating the lowest 2 levels of the transmon. There's a cavity Hamiltonian. Standard harmonic oscillator, A dagger A plus 1/2. And then we have an interaction Hamiltonian. The qubit cavity coupling Hamiltonian is traditionally written like this. So H bar G, sigma plus plus sigma minus, A dagger plus A. And so we have 3 characteristic energy scales: qubit frequency, cavity frequency, and G. And this is the standard Hamiltonian for cavity QED. And so if we're looking at circuit QED, then the typical energy scales that we're dealing with is omega Q of 5 gigahertz, omega C of 7 to 8 gigahertz, and G 50 to 300 megahertz. So that's the circuit regime. If I look at cavity QED with actual atoms, then sort of state-of-the-art numbers, omega Q, omega C, 200 terahertz. Okay, G 0.5 to 25 megahertz. If you are heroic, you can get it a little higher than that, but that's kind of the game. And so so now you see really the big differences in energy scales between the circuit implementation of an atom in a cavity and the atomic implementation of an atom in a cavity. The big difference is in the coupling strength and actually in the line widths. The superconducting qubits can easily have, less than 100 kilohertz of line width. The good old atom is going to be around 6 megahertz of line width. So these are, now that they've been improved, they're narrow and strongly coupled, and these are kind of wide and not so strongly coupled. And so this is one of the reasons why if you actually want to study cavity QED effects, they can often be a lot more visible in the microwave than in the atomic regime where they were originally conceived. And I think that brings me to 1 hour. And so then it's break time and we'll come back and I'll talk about how you use this to actually read out a qubit.